Hey Glenn, so tell me about your trip. I just heard that you're coming back from Japan.
Yes, we just got back from Japan and we had a great trip.
In what sense? Well, what's happened?
Well, the reason we went was the optics group had some metrology issues to resolve. And so along with us, we also brought our reference.
What you mean, like reference to get some sort of baseline towards
Yeah.
surface quality of
Yes.
your mirrors?
Yes,
So,
exactly.
what kind of reference are you using? Like another mirror or something? Or?
It's basically a mounted sphere, and so we have one of our mounts, one of our telescope mounts, and we have a glass piece, of course, as part of that assembly, and that is a very much a known shape to us. We know the shape very well. It's been measured with this measurement system at Coherent, and now we've taken it to Japan.
So Coherent it's based in the US, right?
Right, and Coherent has developed this metrology system, this what we call 2DP. It's a two-dimensional profilometer. It's a mechanical device that we use to measure the surface early in the polishing process.
So why was it so successful? Okay, why?
Well,
Because since you came back, I see you smiling. Okay,
yeah,
so I'm just saying, wow.
yeah. The reason I'm
something's good
smiling,
happened, okay?
well, the reason I'm smiling is this doesn't always happen, and so I always like successes. So we went over there with the optimism that this was going to solve our analysis problem. In other words, when we make this measurement, there's some analysis that goes with it. We didn't understand exactly what the problem was, and so we said, well, let's bring this reference with us and maybe some critical thinking and some measurements, and we'll be able to solve this problem.
Basically, your goal is to get the best surface quality possible.
Yes,
okay?
yes.
So in the end, we get the best. I'm putting my science hat here.
Yes, yes.
We get the best science quality. Okay.
Exactly.
Image quality.
At this point in the process, we're using a mechanical device, and so later on we'll have better optical measurements. But for now, we're in the, let's just say for talking purposes, in the 20 nanometer type range.
Okay.
So nanometer being a billionth of a meter. So we're looking at shape changes of small numbers of nanometers, and we're able to do that mechanically.
Okay, all right. So the same process, you're speaking about Japan, but Japan is not the only partner who's going to actually, surface and polish our mirrors. Okay?
That's right.
So is the same process is going to happen at
Yes.
other places?
Yes, we have, as you know, the mirror is, there's so many segments that we have 4 polishing partners. Now Japan is really leading the way with the polishing, and they've polished 22 of these blanks, if you will, and those will be eventually going to populate the M1. That's the primary.
So these 22 that we can tick them off, they're done, okay, in terms of polishing. Out of the 492.
Yeah, I would say that we need to double check, and that's part of why we were there, really troubleshooting the metrology. And honestly, after we were done, after a couple days of measurements, we had such success that we're basically, high-fiving each other because we had essentially solved the problem.
So this reference sphere, you are going to use the exact same one to do the same check in India and China?
Yes,
and in the US, obviously?
Exactly. So we have plans for this reference to be sort of our master reference for troubleshooting, at least.
You're really talking about roundels, right? So we're not talking about blanks anymore?
Okay.
Can you?
Okay. Let me clarify. It's we in the fabrication process, starting with the blanks, they start out round. When we polish them in the early, what we call stress mirror polishing, we call them roundels, and they're still round. In the real telescope, of course, they become hexagon. So the next step after polishing roundels, we cut it into a hexagon,
and then we call them segments at that point.
And then they're segments.
Yeah, okay.
And then the segments will be integrated with the mount, and they become assemblies. Okay. And so that's the assembly that goes into the telescope.
All right. So you said something interesting here. You spoke about stress mirror polishing, and that's quite unique. Can you explain what's unique about it?
Yes, it's a very, from an optical fabrication standpoint, from my standpoint as a polisher, why I love it so much is because it's an enabling technology that gives you a very smooth surface. And I would probably ask you, why do you care about smooth surfaces?
Yeah, well, because the image quality is all about this. Okay, so and even though we are going to correct images using adaptive optics, okay, at some point in time, and for some instruments, we want to get the best image quality possible even before we apply any correction.
I see. Yeah, exactly. The thing about stress mirror polishing is that basically the process is we bend it, we polish it, and then we release it. It goes into the shape we want. So it unbends into the shape we want. And because of the way we did it, we're going to be able to provide the scientists with a very smooth surface.
Also, if I hear you well, doing this, you need less glass, or you have to get less glass because you want to flex it.
Yes.
And so it's easier to flex if you have less glass.
Yes.
And I put my operation hat this time. Okay?
Yes.
For us, it's good because we're talking about a primary mirror that's going to weight less.
Yes, there's a lot of advantages. The enabling sort of polishing process, the bending of this relatively thin meniscus of clear ceram, this zero coefficient glass, is going to allow for that bend to polish, or stress, what we call stress mirror polishing.
So what's the next step?
Well, next on the calendar in July, we will be going back to Japan, and they will be showing us how they can hex the glass.
Okay, that's a big step.
That's a very big step. And so we have Japan, they're qualified for the polishing, that's great. Japan is also leading the way in hex cutting, and so they will then be able to demonstrate to us that they can take that roundel that they've polished nicely and hex grind it into the shape that we're going to need for the telescope. So it becomes a segment at that point.
Okay, so the same process will be done at all partners, okay, who are actually processing the segments.
Yes.
And no differences, the same instrument. So because basically what we want is to have these segments as identical as possible, whether they come from Japan or China or India. And how are we going to secure this?
The step in the process which really allows for matching, if you will, between four partners. So we have four very strong partners, but to make sure that we're all making the same telescope, the key enabler there is all of these assemblies, whether they're made in India, Japan, China, the US, they all go to the same optical test where we get a very, very good measurement of the surface, and they get their final processing step, which we call ion beam figuring.
So here we're talking about removing one atom at a time, okay, so we get the best surface quality possible.
Right, so the stress mirror polishing, we're going in with a very smooth surface, so it's very good in terms of what we call mid-spatial, very smooth for good science as far as that goes. And we will take some very minor corrective ion figures on the surface against prescription to finish.
All right. And, maybe I was misleading you at some point because I said we want all these segments to be the same. But they are not the same, okay?
That's a good point. That's a good point.
Exactly. We have how many? 82 of them?
Exactly.
Replicated 6 times?
Yes, exactly. We essentially have within the M1 6 of each type. So we have 82 types. We have 6 of each, total of 492 hexagons making the primary.
That's cool.
Yeah, it's very interesting.
Yeah, and some of them are harder to make than others, right?
Exactly right. We're populating the primary. We're starting on the inside. So the allocation for Japan, they're leading the way. They're making those inner segments, which are slightly easier. The allocation ring, U.S., China, and India for the full array, and the ones on the outside are the most challenging. So China and India really have the most difficult segments. They're what we call the most aspheric segments, the most different than a sphere. We have a number of things that are going on at the partners, but with the next trip we believe to be with Japan, and they will show us that they hex cutting a full-size segment. They'll be doing it properly, and they'll give us the data, and they'll demonstrate to the project office that they're able to create segments. And so that if they pass what we call the FRR, the Fabrication Readiness Review, they will have the green light to take those polished segments that have been accepted, we call roundels, and hex cut them very precisely so that they will fit in the puzzle that we call the M1.
So what about meeting again for coffee in 3 months' time? So you can tell me everything about
I think we should. There's a lot going on. We've got things happening in Japan. We also have a lot of things happening in China. We have another partner in China. They are also expecting a review in the summer for their large polishing machine. So there's a lot going on. So I think we really should catch up later on this summer.
All right, let's do this.
Okay.
Thanks, Dan. Okay. How was your coffee, by the way?
Very good.